Director of the Five Counties program, and my email is at the bottom of this slide so that you can contact me if you have any questions. Five Counties program works with Humboldt, Del Norte, Mendocino, Trinity, and Siskiyou counties in northwest California and focuses primarily on fisheries, water quality, and sediment reduction aspects of county roads operations. Before we talk about the case studies for sediment, road treatments, and fish passage, I want to make you aware of some of our watershed planning tools on our website. Our website is at www.fivecounties.org, and I encourage you to take a minute and go take a look at that and see if there's any useful tools that may be of interest to you. The five counties with the counties began a sediment source and migration barrier inventories in each county in 2000 and finished it in 2006. We've completed inventory of about 2,600 miles of the county's 4,100 miles of roads and have identified about 9,600 sites that can deliver sediment to a stream that, and that criteria is that it's more than 20 cubic yards per decade delivery to the stream. As you can see from the graphics, the vast majority of sediment is related to culverts and streams themselves, which makes sense because sediment closest to a stream more of it will reach the stream rather than being trained on the hill slope. But it also points out that there are two types of sediment issues in general. There's episodic and chronic. And episodic sites tend to fail in one storm or in a series of storms. They tend to deliver a lot of sediment. Chronic occurs year over year over year, and this is where a lot of landowners see their erosion. They see rills and gullies on the road surface. They see their cut banks slumping, their ditches filling. And that's one way you can sort of get a sense of that chronic erosion. Within the five counties, in the 2 years of 2008, 2009, and 2009, 2010, the counties have treated about 318 sediment source sites that were identified, and of these, about 174 of the sites were actually related to culverts, and 144 of the sites were related to other aspects of road drainage. But all of the sites collectively disperse water, get it away from stream crossings, restore natural slope, and thus are designed to reduce sediment and erosion reaching a creek. It also gives me a chance to discuss the counties have over 16,000 culverts on the county road systems, and many of those pipes are older. They were installed during or following large storms such as 1964. So the counties have a tremendous aging infrastructure of road-related drainage and are gradually upgrading those crossings and improving them as part of their routine maintenance. We're going to take a look at one of the worst case studies of a county road that was identified and treated. This road has a very long ditch, almost a mile-long ditch. It intercepts 5 ephemeral streams that only flow in the winter, and the ditch itself actually ends up becoming a significant stream. That ditch stream flows down the road. It undercuts banks. It destabilizes the slope. It downcuts the ditch itself, and it erodes away the road surface, which all of these things require chronic maintenance repair to keep the road operable. And you can see that it generates quite a bit of turbidity in the system. And that can be expressed very clearly in this photo. If you look at the left-hand photo where the arrow is, that shows the ditch flow adjacent to the creek on the right of the photo, and then in the right-hand photo, you can see where that ditch is actually being discharged into the creek. So one of the most effective tools for reducing roads-related erosion is to disconnect the ditch and restore the natural slope to the hill slope. So a ditch is a side hill creek, if you will, and an outsloped road, one of the most common techniques, allows the water to run across the road and down the natural drainage pattern. Outsloping roads are the most common treatment you see, particularly for private landowners, ranchers, and forest landowners are using this technique quite a bit. And it reduces maintenance. This photo, the upper two photos are the same site. The photo on the right it hasn't been bladed or treated in after 7 years compared to the photo on the left. So for counties, there are certain limitations of where we can outslope roads. To identify that, the counties put together a design standard consistent with the American State Highway Transportation Officials standards for low-use roads. We call it LIT, low impact to hydrology. And the difference between a county road and a private road is that county roads must remain open year-round. They must be designed for the average motorist traveling at the average speed, whereas a private landowner or a timber company can actually lock or gate or close or not use a road in the winter, for instance, when the surface is very wet or when the conditions make it unsafe. So counties can't locate outslope roads on steep hillsides or on areas that get snow and ice. So we are limited where we can do it, and the LIFT guidelines help provide direction for that. So here's an example of an outsloped road implemented on a county road. This one involved the berm removal as well as outsloping and getting rid of the ditch. One of the benefits of outsloping is that you get a substantially wider road. You also, as I talked about earlier, you reduce the need for maintenance. You don't ditch annually. And many of these roads that you're seeing here, they have not been maintained since they were treated, as many as some of them a decade ago. But again, you can see that the cross-section actually represents the area you're looking at, and you can see that you've gotten quite a bit wider road in the process. Again, here's another example of a county road that was outsloped, and this one has not been maintained. This is actually almost a decade of improvement without having to reblade it. You can see the depth of the fill material that is put in to get rid of the ditch, and there's a variety of ways of outsloping a road. Sometimes you can cut the outside and bring the material to the inside ditch. Other times you're going to actually cut all the way down to the ditch base. Sometimes you're mixing the two. I've seen all of these techniques used. The critical thing for county roads is that they have to be rocked and surfaced after you outslope them, because if you don't, people will tend to ride the inslope edge of the road, and they can actually reestablish the ditch with their real wheel ruts. So it's you need to make a commitment to that. Sorry for this fuzzy photo, but I just wanted to demonstrate that outsloping is not limited to just native or rock surface roads. It is used on some paved roads. You need to be very careful with any drainage treatment where you locate it. This is a site where we outsloped the road, but we actually outsloped it into a poorly compacted fill, and so we had a slump, a fill failure at the site. We've seen 2 or 3 of these in our process, but I just wanted to use this to emphasize that you've got to be aware of the conditions before you modify your drainages, and I'll talk about that a little bit here again. So if you can't outslope a road, there are other treatments to reduce the sediment erosion, particularly related to ditches. I want to let you to this photo on the upper left. This is a bit unusual. That's actually a fill failure on the outside of a road from the berm on the outside saturating and causing it to blow out. But we look to de-water ditches as frequent as possible. 200 to 300 foot would be a maximum ditch length we'd like to achieve if we can do that. And to do that, we installed ditch relief culverts. This set of series is also because of the erosion, the high erosion of these soils. We actually installed an outboard drop inlet into the ditch relief culvert as well, so that we're capturing water that's left by a berm and being carefully discharged, again, tying it into that ditch relief culvert. When you're outsloping or dealing with class 3 streams, it's always best to try to reconnect the channel if you can when you're doing the work. So if you look at the photo on the left, we have an inboard ditch starting at the top of the road in this photo, continuing down, and it's actually intercepting a class 3 stream that you can't really see in that photo and carrying it down the ditch. Now that intercepted creek is going to flow down to another creek where it's going to cause that channel to enlarge because that channel has not historically received that quantity of water, and so it has to adjust, become larger for the increased amount of water. As part of the treatment, we come in, we reconnect the natural drainage, restore the natural class 3 streams into their original channels. We outslope the road. We've now substantially disconnected that artificial runoff from our road system. It does lead me to a point, though. Counties are a linear strip of land. They're not, they don't own a whole area. So when we go in to do a treatment, we only own a 30 to 50 foot right-of-way. For us to install a ditch relief culvert where there hasn't been one for 10, 20, 30, maybe 50 years, we have to get the downstream landowner's permission. With forest landowners, that's usually not only relatively easy, the forest landowners most often encourage the restoration of natural slope drainage. But for smaller landowners who may have developed their backyard because what used to be a channel has not had water for a long time, we may not be able to get a ditch relief culvert or restore a class 3 stream where we want to, in which case we must carry the water further down a ditch. When upgrading culverts, it's critical to try to solve your problems at one time. In the past, pipes were expensive, and so the common practice was to lay them in at a flat slope and as short an angle as possible. This often led to shotgun conditions or a plunge pool at the outlet, as well as pipes that had a high plug potential. So counties, under our road maintenance manual, will come in and they will not only replace the pipe, but they will lay it at the stream channel angle, which is critical to reduce plugging and also to reduce erosion. And we are sizing them to convey the 100-year storm flow now. Many of the older pipes were actually sized for only a 10-year storm. So you can see that this greatly lengthens the pipe, but it reduces your erosion and your plug potential. This particular example illustrates that that same issue. The original pipe in the upper left-hand photo was very short, laid at a flat angle, and actually discharged straight into the bank, which is represented by the solid arrow. When we replaced the pipe, we realigned it to the natural channel, which is the dashed arrow. The center photo shows a bit of an unusual treatment here. This is the inlet of that pipe. This is a class 3 stream, and we used a rock mulch. There was no riparian habitats or aquatic beneficial uses in this area, and quite a bit of fine sediment. So we actually use this rock to entrain that fine sediment in the first years of construction. This isn't a technique you would use everywhere. The middle photo also shows an example of the diversion potential. This is a switchback turn in a very steep gradient road. And in the previous condition, if this pipe plugged, the water would divert down the road and continue down the road to the next channel or jump off the side and cause significant erosion. To address that, the lower photo shows a critical dip or a return flow located at the just below the hinge point of this switchback, so that water that would divert out of the crossing should it plug will now be carried back and directly into the channel, reducing the potential for significant erosion and diversion down the road. Again, sometimes to install a pipe correctly means a significant increase in length. This photo shows a very short pipe set at a flat angle in the left-hand photo. It shows a plunge pool at the outlet and then a substantial drop. The middle photo shows us excavating out the old pipe, and the right-hand photo shows the extent of work needed in this particular case to carry that pipe down slope. I believe this pipe actually ended up being both larger and 80 feet longer. You'll note the large riprap rock slope protection on this one. This was a debris slide above the road, and so it required some substantial additional armoring to protect the crossing. But the key is that getting your pipes down at the channel grade that you need. So now I want to talk a little bit about plastic or metal pipe and downspouts and energy dissipators. So which one is the appropriate one to use? Plastic has a lot of advantages. It's very lightweight. It takes fewer people to work with. It tends not to be quite as sharp. You need less equipment, and it's also less expensive to purchase. So a lot of people are looking to use plastic versus metal. The downside to plastic is in fire-prone environments. And if you only have one or two pipes on your property, and you're going to replace them should you have a fire that burns up those pipes, then they're a very viable tool. If you own a lot of pipes, such as counties, and you're in fire-prone areas, you're going to have to weigh the ability to come back in and restore those watersheds in the event of fire compared to the durability and fire resistance of a metal culvert pipe. I can't tell you which way to go, but those are factors you need to think about. Switching away from outsloping and ditches and class 3 streams for a minute, I want to talk about through cuts. Through cuts are road segments that are essentially functioning as creeks. The cut bank is higher than the roadbed. The roadbed is lower than the berm on the outside. In these areas, water concentrates in the through cut. It affects the structural integrity of the road base itself. You get significant rill, gully, and rutting. It's almost impossible to drain your through cuts, and they can be a significant connection to stream courses. So one of the most important ways to deal with through cuts is to get rid of the berm. Again, in this case, we outslope the road, and we use geofabric. So you can see that we're testing the use of geofabric to see if it can reduce cost. One of the advantages of the geofabric is that if you have low-grade rock or you don't have a sufficient rock source, you can get away with using a little bit less rock on your road surface because it's not going to sink through. And we are, as I said, we're doing a study on this to determine if maybe there's some cost savings with expanding the use of geofabrics in these type of conditions. I'm going to switch gears and talk about our fish passage component at this stage. The 5 counties that we work with did a barrier inventory. We have treated 60 barrier sites in the last decade. 70 sites total. 10 of those have been with non-county entities. We spent about $16 million in barriers and road-related treatments. We restored 147 miles of habitat, and the counties have used over 15 different designs for their barrier sites. I'm going to talk about, or at least illustrate, 9 of those types of techniques here shortly, and we have at least 24 high-priority barrier sites remaining. As you can see in the photo on the right, this is Morrison Gulch in Humboldt County and the spawning response. Removing barriers has been an important component in restoring coho and steelhead habitat throughout our counties, and pretty well documented in that chart. Down on the lower left, this is a precast concrete bridge structure representing one of the types of construction we used. Most of our barriers consisted of culverts that end up with a perched outlet, and so we restore those. Some sites, such as a site that can convey the 100-year flood already, but still has a perched outlet, can be treated with a retrofit design like you see on the left. A metal arch with an embedded weirs is another one. One of the problems counties have is they only have this very narrow right-of-way, and you can have very steep drops, such as you see in this photo, and you have to convey your grade change through your very narrow right-of-way. So they use some innovative techniques to try to capture that grade change in a very short distance. The photo on the right is a concrete vortex weir. It's a fairly complex design, but again, steep grade change is what drives the design criteria. The photo on the left in this slide is a metal arch with concrete head walls. This is one of the more common types of structures that you've seen the counties use. And all of these structures are designed to convey the 100-year flow with bedload and debris. So as you can see in this upper left-hand photo, you've got a lot of wood jamming the inlet of the pipe, and the one below it shows the ability of that crossing to convey the wood. The concrete arch with national span or conspan being the two most common ones that we've used are probably the single most common barrier removal and replacement structures that we have. And then you have this very complex post-stress concrete bridge, which is over 100 feet long, representing one of the more complex types of barrier removals. In addition to addressing fish passage and flood and bed load, almost all of these projects also result in providing for large wildlife movement and migration. And we've actually seen empirical evidence of decreased mortality for deer and bear when we've replaced barriers. Now I'm going to look at a couple of projects in more detail. This is Little Browns Creek. I'm going to call this the Hollywood production because it's very big, very complex. As I was telling you, the counties have a very narrow right-of-way, and they have to convey the grade change in a very short distance in most cases. This particular project has an 8-foot drop, and being able to convey that grade change within the county right-of-way was not possible. So this project actually involved reconstructing an entire channel. I also want to point out where you'll see the red arrow. That's this is 3 culverts, 48 inches in diameter, all of them clearly undersized for the crossing, and you can see this large boil hole off to the side that formed as a result of the energy being created as water's hydraulic through those pipes. So here you see a design. This project actually included reconstructing 350 feet of stream channel, which was necessary to catch the grade so that we could allow fish passage. So the project is a poured-in-place concrete bridge, kind of your old traditional bridge construction technique. It has sheet pile footings, and then you can see them forming and pouring the actual bridge structure. So that's the crossing. But in this particular case, upstream, those 3 small pipes had resulted in a lot of sediment dropping out, and instead of having your normal stream channel, typical for these areas would be a stream capable of carrying in the channel a 2 to 5 year flow before it would go over bank. This one spread out and resulted in the creek drying up early in the summer. So to address this, the decision was made to actually reconstruct a more natural channel. And you can see in these photos, the lower left is building the base for the channel, which I believe was approximately 10 feet wide at the bottom, and then laying the So building the channel also requires restoring a stream bed mix in the channel. And so you can see here we're setting grade control ribbons. These are subsurface, subterranean grade control structures that are set and then actually having to place a stream bed. So to continue into that, you can see the roughened channel, as it's called. You can see these grade control ribbons with the elevations for them set. Right below that in the lower left, you see 2 rocks that form constriction points. These are set every 25 feet in the channel, and the ribbons were set 25 feet also. So you have a ribbon and 2 constriction rocks, and then another ribbon downstream. Once all of those subterranean items are set, you need to come in and actually build a stream bed, so you can see us working on bringing that material in and getting it in place. Once you have a stream bed, you need to have stream banks, and so the decision was made to mimic natural systems and use bioengineered willow-based stream banks rather than traditional rock slope protection alone. So here you can see the process of building brush mattresses and fascines. The mattress is laid down, and then the fascine is this willow log which is set at the base of the fascine to hold it in place until the roots can grow and establish the engineering strength. This particular channel doesn't have much large wood, so another component of this channel reconstruction was the installation of large wood components, these large wood groins, if you will. And you can see the channel's wet because part of the process of building a channel is to jet the fines into the gravels and the cobbles and the boulders that make up a stream bed bottom. And so there is a very aggressive jetting process. Here is what the channel looks like. Once you've constructed it, you can see in the upper left building the bioengineered stream wall, the center photo showing the large wood placement with the jetting of the soil. Once the bioengineered willows are in place, you need to bury them, showing this photo in the upper right, placing material. The lower left is the jetted stream channel with the bioengineered willows ready to go. And lower right is the photo of the site a couple of years after construction. And you can see from the reference arrow the same. This is what the channel looks like during the first year after construction. What it looks like looking downstream to the crossing and upstream in the now reconstructed channel. This total project cost about $600,000. We have a commitment to long-term monitoring of the site, and as you can see, there's 5 years of channel surveying that will indicate that actually this one is pretty stable. The design worked, and we did not see any significant alteration of the channel bottom. We also were successful in documenting fisheries upstream, which was obviously our criteria for the original project. So we continue to monitor this site. Now I want to switch gears. I want to go to, if that was the Hollywood production site, I want to go to the home movie site, if you will. This is a small stream. It's immediately adjacent to the one we just looked at Little Browns Creek. This is a tributary Finley Gulch. It didn't really show up on anybody's radar as a fish-bearing stream, but we had noticed it and noticed that it was both very cold water temperatures, and there was a very large resident trout and steelhead population at the outlet of this pool. So we investigated further upstream, and we found that this creek has year-round flow or has year-round pools, a number of year-round pools that are very cold in 54 to 58 degrees in the summer and provide important potential refugia for steelhead. So we decided to take it on and open it up so that fish could move upstream into those cold water pools. The other reason is that we had noted in the spring that there were up to 50 small fish in this one pool downstream of the culvert, and by the end of the fall there were only 2 or 3 happy larger fish. So we knew predation was a significant issue. One thing I want to talk about is that in all of our barrier sites, and Kirk alluded to this, there's always a pool at the outlet. And when we're done, we get rid of that pool. This site actually gave us the opportunity to try to experiment to see if we could retain an outlet pool in the process. So we used an unusual technique for it. Being a home movie, the other sites have CAD drawings. These were done with an Excel spreadsheet, but you can see the design objectives in here. You can see the channel gradient. So here we go. We have a 42-inch diameter pipe in the upper left-hand photo. We're going to excavate that out. We're going to install an 84-inch pipe or a 7-foot diameter pipe that's going to be embedded in the bottom with a natural stream bed mix. And in the lower photos, you can see a metal plate arch, V-notch arch that we installed again. This is to try to create enough scour energy to maintain an outlet pool. And one thing I want you to look at in all of these photos is the water quality of the pool. In each photo, you'll notice that the pool was well protected throughout the construction until you get to the one with the red arrow, and you'll see that that's very turbid. I'll talk about that here shortly. And after the project is completed, you can see the first flows and then the first storm flows following that. Again, the objective was to try to maintain a bit of an outlet pool. So in any of these embedded culvert projects, you're going to embed natural stream bed mix material. So here you can see the V-notches on the outlet end, loading material into the culvert on the inlet end, and then in the upper right-hand photo, they loaded the culvert up on a Friday night, plugged the inlet, and then left for the weekend, which caused me no comfort throughout the weekend. Luckily, it was a good weekend. Come back Monday morning, we used a backhoe with an extender hoe to get the stream bed design material pushed into the pipe. And once we had it in there, we dropped in a little tractor to help position it, move it around, spread it, and we worked on jetting. Now I want to talk about jetting. Once you've got the material in, out comes the little tractor, and then you jet the fines into your gravel and cobble mix using a very high pressure hose. And this is a critical element because now you're creating a lot of turbid water that you've got to manage for. So if you look in the lower photos, you'll see that jetted fine turbid water at the outlet is being constantly pumped out and both recycled back in to use for more jetting and also discharging in a place that will not let it get back into the creek, which you can see in the upper right. So this jetting process is done to seat the fines, but it also has to be done so that it protects the creek. And you can actually see in the lower middle photo the process of pumping and moving water. The lower photo shows the first large storm after the culvert is put in place, and the jetting actually worked very effectively. We saw almost no fines. But here's a quick synopsis of the entire project again. Excavation, placement, you can see in the middle level left-hand photo, that's the original channel bed. That's the channel we tied into with the embedded material. And you can see the first storm that winter following in the. So this project cost under $30,000. We are still watching. It's been a few years. We're looking at the effectiveness of the V-notch to create a scour pool and keep reporting on that and how effective it is. The counties have a road maintenance manual. I showed it in our second slide, and as part of that, counties undertake a number of activities and trainings to address water quality and improve fisheries, and so I wanted to take a second to illustrate some of those. This upper set of photos show a county where a large cottonwood was washing downstream and potentially threatening a bridge, and the county, instead of pulling the cottonwood out, actually pushed it over to a bank downstream. And in the photo to the right, you can see that cottonwood sprouted and actually created a nice. Similarly, in the middle photos, you can see a stream bank being washed away, and the county used a bioengineering and rock slope protection combination to both protect the road and to improve the habitat. The other four photos in here demonstrate some of the combination the 5 counties can work with. The actual counties, we can experiment with techniques. This was actually a project where we wanted to see if bioengineering would work. We experimented with it before we recommended it to counties. It worked highly effectively, and we're seeing the counties use these techniques more and more all the time. I want to change gears for a minute and talk about climate change as it relates to road maintenance and road upgrades. That this is becoming an important component and consideration of what we do. This issue arose, so we took a look at Weaverville, California, where we had a 115-year rainfall record. And what I want to show you here is the change in the type of rainfall. The actual average rainfall never changed over the last 115 years, but the nature of the rainfall has. So if you look at this graph, you'll notice that between 1895 and 1932, there were 4 years in which the average annual rainfall exceeded 50% above or 50% below the average. So in other words, these were very wet or very dry years based on annual rainfall. Between 1932 and 1971, there were only 2 years in which the average rainfall exceeded 50% above or 50% below the actual average rain. Sorry about that, confuse you. Beginning in 1971 to 2009, the period that we looked at here, there were 9 periods where the average rainfall exceeded that 50% threshold. So over the last 115 years, what we've seen is a more frequent greater rain or greater drought conditions. And these in turn translate into road management problems, because if an area burns, it's going to have much higher runoff shortly after that. And if an area floods, particularly after it burned, you're going to see quite a bit of downcutting in the stream channels, a lot of materials moving, a lot of stress on your road system. So I'm not going to go into this to any great detail. I'll just refer you to the websites that I have at the bottom of these slides. You can take a look at them if you're interested. But it does mean for us that we need to think about that when we size our. That, I believe I've concluded my presentation.